Hello, friends. This is a quick overview of the speed of sound. Sound is a wonderful topic, a wonderful wave. It's really cool. Watching sound, if you can visualize it or see it, is really cool. And hopefully I can show a video or two of it. The speed of sound is surprisingly, audible, meaning an echo shows that, there's a delay between when you speak and there's a wall, right? Right. And then there's some wall or a canyon, and then the wave comes back. Or in a stadium, you have two speakers on opposite sides of the stadium. There's a delay between one speaker and the other. So the speed of sound. Sound is a compression wave or a longitudinal wave. I please invite you to look at the link of the animation, the GIFs that I showed in class. Think back, when did we show that? Yes, I posted it with the homework on Google Classroom. Take a look at that. It's the one where like you have the dots close together and then they're far apart and the dots close together and then they're wiggling back and forth at some frequency F. A single particle, a single molecule in the air is wiggling back and forth, but the wave, the compression, moves forward at a speed v. Again, two completely different things. The shape is a compression. It's not a crest. A transverse wave is where you have a crest moving forward at some speed v, and the molecules go up and down. Here, the molecules go back and forth, and the compression moves forward at a speed v. The speed of sound in air is 343 meters per second, and that is 20 degrees Celsius. The temperature matters. So I'm going to overview right now. Now, here's a few caveats. You should know this number, 343 meters per second. It's like a third of a kilometer per second. It's about a fifth of a mile per second. So if you count to 5 after you see lightning and you hear the thunder, it's a mile away. Every 5 seconds is a mile away. That's where that comes from. That's the speed of sound, because you see the light almost instantly. The light is crazy fast. We'll go over that speed eventually. It's not instantaneous, but it's almost instantaneous. It's like a fraction of a second, but the sound takes its time. 5 seconds later, it hits your ear. Boom. Boom. Literally. So where does this come from? You're going to calculate it on your homework. I'm going to give you the formula right now. Here's the point. The velocity of sound in air is always less, or let me go back. Through any gas is less than the velocity of sound through any liquid, which is less than the velocity through any solid. This I want you guys to know. So more solid is faster. That's like the takeaway. If you take away anything from that, I want you to know the number, right? Definitely need to know the actual speed of sound, and we're going to calculate it tomorrow through different materials. On your homework, you're going to calculate it through different gases. And next week, we're going to use those numbers to see how this manifests in real life. So it's kind of fun. It goes deeper than you might have known. Literally, deeper into the earth is where we're going to go. I revealed the secret. It's okay. Gas, liquid, solid. Why? We want to know the mechanism. What is the mechanism? In this class, you might have already noticed, we want to go deep into the stone, right? Not just know its weight, not just know what it's made of, not just like say, okay, here's what it is, here's the information, not just use the information, but we want to know why. What is going on? Let's go deep inside. Let's find the truth, the patterns, the deeper connections at play. So I'm just going to sort of briefly in this video outline them. I'm going to maybe discuss them more detail in class, but I'll make this video short and sweet. So if you have questions, bring them to next class. But here's the information. The reason why is, if you recall, here's the concept. This is hugely important. I'm giving you gold right now, golden wisdom. This is the simplified concept, right? Velocity depends on medium, or on the medium, or depends on properties of the medium. What properties specifically? Tension or equivalent? Or connection between particles. This is between. This is my way of writing between. Oops, put an extra L in there. Connection between particles, and then, of course, density. This makes velocity go up. This makes velocity go down. Sorry, I don't know if that's confusing. I feel like that's, to me, that made sense, but I can see that being potentially confusing. More connection or more tension, or a stronger connection, and this will make sense in a second. This is the quick way to group it in your mind. It's so simple. It's about, are the molecules connected more? Cool, that's faster. And we know that in a slinky, tension makes it faster. But what's the equivalent of tension in the air? Turns out that's temperature. That's the connection. I'll just say it. It's temperature, which is cool. It starts with a T, so it's easy to remember. But those are two completely different things that happen to facilitate the same result. The tension is the connection physically of the metal molecules. The temperature is how gas molecules connect to each other. And I'm going to briefly overview temperature, just enough so you have an idea. You might have more questions. We'll do thermodynamics later. Hopefully this will be just enough to have it make sense. At minimum, please you can just memorize for now. Temperature is the connection between gas molecules. So more tension. What do you want? Bullet point, star, I'll do bullet point. More tension, and then obviously more density or more mass is slower. So you might say, wait a minute, what about in like a liquid? Like water is more dense than air. Yeah, but it has intermolecular forces. Whereas air did not have any connection, it just has temperature. Right? You have those hydrogen bonds that you might have heard of in the H2O molecule, right? Where the valence electrons connect with the positively charged hydrogen in another water molecule. Isn't it cool? So that they're connected via, which is really just the electric force that manifests in a tension. Right? I mean, it even has a name, surface tension, if you're just looking at the surface, right? It's manifested in something called viscosity, although that's friction, so that's a little misleading. What it's really manifested in intermolecular forces. So water's a great example. The intermolecular forces, which I'll say IMF, are intermolecular forces. There's a term for that. It's called the bulk modulus. Isn't that such a cool term? So the stronger these intermolecular forces, the bigger the bulk modulus is. And the unit of bulk modulus is actually force per square meter, because what you can think of as like, okay, here's a molecule and it's exerting a force, but it's distributed over an area, a square meter. And because we're thinking in 3 dimensions, you can think of this force kind of going in all directions. And you want to think about how is this force distributed over the area around the molecule? How is it pushing and pulling on everything around it? We're not talking about 1 dimensions here, guys. This is 3D waves. Right? So we have a molecule pushing in all directions. We want to ask, how is it pushing and pulling, not just linearly, but in the entire sphere around itself. So we have a sphere, like just a made-up sphere. We have a water molecule here, or a metal molecule here, and we want to know, how is its force distributed over that region around itself in 3 dimensions? Because we're dealing in 3 dimensions here. It's not just a linear tension. In a string, it's just tension, it's a vector, but here it's a distribution over the surface surrounding it. So it's force per square meter. I hope that makes sense. You don't need to know that too much. Again, if that's too crazy, just remember that it is. And it's okay. If you don't understand it, it's okay. But if this helped, great. I hope you heard what I just said. If this doesn't make sense, it's okay. At least remember that bulk modulus is the tension in a 3-dimensional wave. Pause, let that sink in. And use the letter B for bulk modulus. I love that term. Bulk modulus represents the tension, which is literally the intermolecular forces between molecules in any substance. Now, gases don't have. And again, we'll go over this. Don't have intermolecular forces. Everything's kind of related. So it's like, what do you talk about first? Gases are assumed to just be particles flying around at random speeds. And the faster the speeds, we call that temperature. Temperature is the average kinetic energy. You may or may not have heard this before. If you haven't, that's okay. I'm telling it to you now. We're going to go over this in great detail in thermodynamics. Have some fun looking at all of this. It's a really great study. But for now, just know temperature is the speed. And it's the way that, remember, it's all about information. How does this molecule connect to this molecule? Well, it flies into it at a certain speed. So higher temperature means higher speeds of the molecules, which means a higher speed of the wave. Right? So if I wiggle this molecule back and forth at some frequency, it's going to connect with this one faster. Now, to me, because of the random motions, it's kind of like harder to picture this. It's easy for me to see 2 things connected by a tension. So I get it if you're like, this picture doesn't make perfect sense to me, but it is the way that it is. It's been measured, it's been theorized, it's been modeled. I agree it's harder to draw and visualize. But the point is they don't have intermolecular forces, so temperature is the connection. And to me, I feel like that I get that. That makes sense. I'm going to be honest about things that I already have been. You might have noticed things that make sense to me that I can visualize, things that are a little more challenging. This is more challenging for me to visualize, but conceptually, that makes sense to me, and I hope it makes sense to you that the only way for these 2 to connect is by one flying into the other. Because gases, the molecules are so far apart, And I'm assuming you may have heard gases, liquids, solids, and the difference between the three before. Gases are assumed to not have intermolecular forces. If you have not heard that, here it is. They are that. And if you have any questions, feel free to ask them in class, although we might have to save it for thermodynamics. We'll talk about this more. The point is temperature is the connection. So those last two slides are a big deal. So liquids and solids have more density, but they have stronger intermolecular forces. Which wins? Well, we already know the answer. The intermolecular forces wins. And we're going to see those calculations on Thursday and in the following week or two. We're going to do calculations. I'm going to give you bulk modulus and density. I'm going to give you temperature and molecular mass. And we're going to realize that temperature is a really bad connector compared to bulk modulus. The bulk modulus will be in the billions. The temperature will be in the hundreds, just to give you an idea. Bulk modulus is crazy strong. Temperature, not as good. So the IMF wins over density. So these are more dense, but stronger IMF. Please know that. I'm gonna do orange bubble, but stronger intermolecular forces. That takes too long to write, so I'm gonna write IMF. Cool, great. Pause, write a question down. It's a video, easy, done. Ready? Last thing. So, equations for a gas, the speed of sound, whether it's air, whether it's helium, carbon dioxide, hydrogen gas. We're going to do a few of those gases that actually exist. Sound moves differently through them. If you breathe in helium, your voice changes because the speed of sound goes, I'll just say, faster in helium. Why faster in helium? The reason why faster in helium is because it's lighter. This is the molar density or the molecular mass. Again, you don't have to necessarily know what this is, although I'm assuming all of you have had a little bit of chemistry, and I think you might talk about this in biology. You should know the molecular mass is listed on the periodic table, right? Either way, it's how heavy the atom is or how heavy the molecule is. It's grams per mole, but I'm going to convert to kilograms per mole because we need kilograms. Chemistry, you sometimes use grams. Physics, we got to use kilograms. So pause if you need to rewind, go back, listen to what I just said. We need kilograms per mole. So I'll convert it for you, or you might have to convert it, but you know how to do that. This is the most tricky one. This is called the adiabatic constant. It's also the Greek letter mu. You might say, what word? Adiabatic? There's no way to explain that right now. That takes a minute, takes a day or two. It's almost insignificant. The adiabatic constant for air is 7/5. The adiabatic constant for helium, I think, is 5/3. Don't quote me on that. It's on your homework. They're just numbers I'm going to give you. I will give you these. One day, if we get that far in thermo and we talk about adiabatic processes, this is going to be awesome when we discover what this is, because it's really cool. It has to do with their vibration modes and the information stored within the air molecules in the helium. It's a very thermodynamic quantity. The point is, I'll give you them. You don't need to know what it is yet. Just need to know its value. You're just going to plug it in. It depends on the gas constant, which you might have used in chemistry. Again, we need joules, not and meters, not liters. So it's 8.31 joules per mole Kelvin. So going back to temperature, I realized I forgot something. Okay, so here it is. The unit of temperature is a Kelvin, where Kelvin is Celsius plus 273.15, meaning that 20 degrees Celsius, right, equals 293.15 Kelvin. Again, I'm going to give you that. When we do thermodynamics, you're going to need to know that very well, that Kelvin is the relationship to energy, not Celsius. Celsius just has to do with water, but Kelvin is absolute to the universe. It's the absolute temperature scale that applies anywhere. It just doesn't apply to humans that well, so we don't use it in our everyday lives. We use Celsius, and Fahrenheit's more economical or political, how that was invented for social morale. We can talk about the history of those three scales when we do thermal, but just know that we need Kelvin. Right? And this, again, I'm giving to you. Notice I'm giving you these numbers. You don't necessarily have to know what they mean, but I do want you to practice plugging numbers into an equation and seeing what you get. And last but not least, temperature. So notice the point here. We have temperature on top, the connection. And what do we have on bottom? Density or mass. Tension over density. That's gas. Pause and go back if you need to write that down. Solids and liquids. The velocity of sound through any solid or liquid is the square root, this one's easier, of the bulk modulus over the density. Again, these are the intermolecular forces, the tension between the molecules. And then this, of course, is literally density. I brought this up in class. This is the Greek letter rho. It's mass per volume. It's called volumetric density. The unit, therefore, is mass, kilogram over volume, which is cubic meter, not liter, because we need meters, right? Again, I will give this to you. We'll study this more in fluids. I'll just give you the densities. I'm going to give you the bulk modulus. You're just going to plug it in, right? You're just going to plug in these values, and out comes the speed of sound. And we're going to realize that this is way, way faster than in any gas. And that has everything to do with the fact that this tension is huge. The connection between molecules in steel, in any metal, even in water, is much bigger than the random far apart motions of gas molecules. That's it. I hope that worked. I try to keep it brief, but as you can see, I love talking about this. So bring your questions to class. Again, I want to emphasize one important thing. I'm not expecting you to know the intimate physics of these things yet. I'm asking you to think about it, though. Ask great questions and understand it's connection divided by density. That's the simple thing. Connection divided by density. And then if I give you numbers, can you plug them into an equation and tell me what number comes out? Can you use these equations without necessarily fully understanding everything? Or do you want to ask questions until you fully understand everything? Eventually, we're going to cover all this stuff. So I'm happy to talk about it. Right? I hope you see the balance game I'm playing. Either way, have a great rest of your day. See you, class.